Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. What we're doing is the history of mathematics. We're going to do congruence modulo M part 2. This lecture specifically, what we're going to do is we're going to do divisibility tests. We're going to do Ceasar ciphers, and we're going to do the Enigma Machine ciphers and how to use congruence mod M to describe the Enigma Machine cipher and Ceasar ciphers. Let's get to it. All right, Alice wants to know about divisibility tests too. So the first game we're going to play is divisibility tests and the remainder game. The remainder game will play first, and then you'll see why in a lot of the cases if they make you play this game, this is why we want to generalize this game to writing n as coefficients multiplied by powers of 10, so it'll be 10 to the k, and then we're looking at dividing 3, say, into powers of 10 to the k, and then we want to get divisibility tests for positive integers. This will be the game. First, what we're going to do is we're just going to look at an integer b to the k, so b is some base, and then we're going to have some exponent k. They're both positive integers, and what we want to know is when we take another integer m, which is larger than or equal to 2, when we divide b to the k by m, what's the remainder that we get? What we're going to cleverly do is we're going to either try to find what b to the k, hopefully b itself will be in the class, congruence class of either 1 or minus 1 modulo m. If it's not, I try to find the first exponent or power of b, which will give me in the congruence class of 1 or negative 1. I'll focus on 1 for now, but you can use negative 1. And then after that, we can use clever arithmetic to get at what the remainder of b to the k is. Let's do that specifically. All right, before we get started, we have to do a theorem on modular arithmetic, and then we can use all of these properties to do divisibility tests and solve the Enigma machine. All of these, we need to know if we can add to on both sides of these congruences and subtract, and this is what it says. The two most important ones are going to be number 6 that we have to be careful about, cancellation, modulo m, and doing powers. This will be extremely important when we do divisibility tests. A to the k will be congruent to b to the k, so we can change big numbers into small numbers is what this is going to say when we're trying to compute using this black magic. So the first ones are going to say basically that we can add on both sides of a congruence if we want, and you can subtract on both sides of a congruence if you want. Also, you can add on both sides, so if a is congruent to b and c is congruent to d, then we can add the a and the c on the same side, and that will leave the same remainder as b plus d. Remember what this is saying is if a and b leave the same remainder when I divide by m, and c and d leave possibly some other remainder when I divide by m, then when I add these numbers, a plus c will leave the same remainder as b plus d. Similarly, if you have these two congruences hold, you can subtract them and this still is valid. Another one that's going to be extremely useful is if a is congruent to b mod m, you can multiply on both sides by c, and this will give you a times c is congruent to b times c mod m. The one that we have to reverse is we have to be careful if we want to cancel c, essentially, is what we're going to try and do. If I want to do that and get rid of it to here, what you have to have is the greatest common divisor of the thing you're trying to cancel, and the modulus must be 1 in order for this to work. Otherwise, it might not be true. And if we have that a is congruent to b mod m and c is congruent to d mod m, you can multiply on both sides, just like adding, and the remainder will stay the same. And in particular, as a consequence of this, using mathematical induction, we can prove for every positive integer k, if a is congruent to b mod m, then a to the k is congruent to b to the k mod m. This will be extremely useful for our divisibility game. Let's get to it. Okay, what we're going to do is we're going to try and find the remainder of 2 to the 431 when I divide by the number 5. Yes, I just picked the numbers 1, 2, 3, 4, 5 and rearranged them slightly. So we're going to do 2 to the power 431 when I divide by 5. This is some horribly large number, and we are never going to be able to long divide and use a quotient or remainder or use a calculator. What we're going to cleverly do is use the black magic arithmetic and get at them this way. First of all, what I need to know is this. I want to know 2 is congruent to itself modulo 2. So the first thing I need is to find the first power of 2, which leaves a remainder of 1 when I divide by 5. How are we going to do that? I'm going to look at the powers of 2 specifically, and then I'm going to look at the remainder of those powers of 2 when I divide by 5. And what we're going to get is we'll get a table of values, which I can use, and then we're going to do this. So let me write this out, and then we'll find a pattern, and then somewhere out there is our number, 2 to the 4, 3, 1, and we want to know what our remainder is. This is the box we're trying to fill in. That's the answer. Whatever number goes in there is the box. So what are we doing? We can do 2 to the 1, 2 squared, 2 cubed, and so on. Dot, dot, dot. Notice we can have infinitely many powers of 2s, including this one, but there's only going to be 4 non-zero remainders when I divide by 5. 1, 2, 3, 4. We're never going to leave a remainder of 0. So first of all, I look at 2. 2 leaves itself or its own remainder when I divide by 5, so good. 2 squared is 4, which also is less than 5, so leaves its own remainder when I divide by 5. But now we get 2 cubed, which is 8, is congruent to 8 minus 5 is 3 mod 5. So 2 to the 3 leaves a remainder of 3 when I divide by 5. And now I can start using this arithmetic trick. 2 to the 4 is congruent to 2 times 2 to the 3, which is 2 times 3, because 2 to the 3 is congruent to a 3 from the previous line. And then I get, this is a 6. 6 minus 5 is, oh, that's what we were looking for, a 1. So now I get the first power of 2, which is congruent to 1. Well, we got to let the kitty down. Kitty. Oh. We found the first power of 2, which is congruent to 1 modulo 5. And now if you look, this pattern will just repeat itself over and over again. Dot, dot, dot. So we want to know where we are here. Now what we're going to do is we're going to try and find, because I know 2 to the 4, I'm going to look at the 4. What we're going to do is divide 4 into our exponent, 2, 4, 3, 1. So I have 4, 3, 1. I'm going to divide 4 in there. 4 goes into 4 once. I get 4. I subtract, I get a 0. I get a remainder, I get 3. 4 goes into 3 no times. I get 0. I subtract, I get 3. 31. 4 goes into 31 how many times? 7, which is going to give me 28. Minus, we're going to get 3. So we get a remainder of 3. Now what I'm going to do with that is, this says 431 is equal to 4 times 107 plus a remainder of 3. Now when I exponentiate that, 2 to the 431 is congruent to 2 to the 4 times 107 times 2 to the 3 using exponent laws. Then I know that 2 to the 4 is congruent to 1. This is modulo 5, now we're computing. But I now know that I can use the black magic arithmetic and turn 2 to the 4 into a 1 to the 107 times 2 to the 3. We also know, I'll go slow, mod 5. So the 1 to the 107 is a 1. That's going to be gone now. And what is 2 to the 3? 2 to the 3 we found out left a remainder of 3 when I divide by 5. So what that says is 2 to the 431 and 3 leave the same remainder, i.e. the remainder is 3 when I divide by 5. The remainder that 2 to the exponent 431 leaves when I divide by 5 is the remainder 3. It had to be one of 2, 4, 3, or 1. And we found using this black magic clever arithmetic that the the remainder is in fact 3. Let's do another one. Okay. Kitty, kitty, kitty. Yeah. Was that good? Yeah, that's good. Oh, that's good. All right. I gotta do these myself, so I gotta need coffee. Mathematicians make coffee into theorems, basically, so the saying goes. Divisibility tests. Now that we know the game of playing this arbitrary power game, it seems like we're chasing our tail, but it's not going to be. What we're now going to do is, now that we played the find the remainder when b to the k is divided by m, what we're going to do is specifically rewrite all positive integers in decimal notation. So like this, in strings of decimal digits. And what that really means is they're placeholders for multiplying that decimal digit by a power of 10. And then we're going to have a base 10 to the power k, and we're going to try and divide by numbers, say like m equals 2 and m equals 5. And all the digits are going to be from 0 to 9, and these are going to be our decimal digits of the number n. And then what we're going to ask is, when I have n, or specifically powers of 10, when I divide by 2 and 5, what are the remainders that I get? And so it turns out for 2 and 5, this is really easy. And classically, this is called casting out 2s and casting out 5s or casting out 9s. Whatever we're casting out is we're trying to find a divisibility test for these things. All right, so for 2's, what we notice is note, and why we can do them at the same time. 10 is 2 times 5, so this says that 10 is congruent to 0 modulo 2, and 10 is congruent to 0 modulo 5. Then from our modular arithmetic theorem, property 8 tells me that if A is congruent to B mod M, then all powers of A are congruent to all powers of B mod M. So this says by our theorem part 8 that 10 to the k is congruent to 0 to the k, which is always 0 mod 2, and 10 to the k is congruent to 0 to the k, which is always a 0 mod 5. So all the powers of 10 leave a remainder of 0 when I divide by 2 and 5. This shouldn't be surprising. 10 is 2 times 5. What is that going to do for us? Now that we have this scenario, look what we can do with n. So for the 2's, casting out 2's, we therefore know that n is dk 10 to the k plus dot 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 plus d1 10 plus d0. Now if I hit that modulo 2, all of these are zeros. This is dk times 0 to the k plus dot 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 plus d1 times 0 plus d0. He's the only one that doesn't go away because he doesn't have a power of 10. Modulo 2. Therefore, all of these are going to go away. We can cross them all off. And I'm going to get, this is congruent to, n is congruent to d0 modulo 2. What does that say? What's our original definition? A is congruent to B modulo M if and only if A and B leave the same remainder when I divide by M. That's M is 2. That's a 2er. So what does that say? N and its last decimal digit D0 always leave the same remainder when I divide by 2. 2 only has 2 remainders, 0 or 1. So in particular, 2 divides N if and only if 2 divides the last decimal digit D0. And this is where we get casting out 2's or the test for 2. This is exactly the same as true if I replace the 2 by a 5, because we know that this is also true. So because of both of those being true, n is also congruent to d0 modulo 5, which says again that n and d0 leave the same remainder, d0 being the last decimal digit. N and d0 leave the same remainder when I divide by 5. In particular, the last decimal digit is divisible by 5 if and only if n is divisible by 5. And the only 2 single digits in here which are divisible by 5 are 0 and 5. So we now have a theorem which we've proved essentially rigorously that a number n is divisible by 5 if and only if its last digit is a 0 or a 5. Let's write those 2 tests down and then we'll cast out 3's. You can cast out 9's on the homework assignment or just for fun, I'll make you do it at the end. Let's get to this. So what does this tell us? We have our first 2 tests. This says that 2 divides n if and only if 2 divides d0, the last decimal digit, and that's if and only if we can write this explicitly, d0 equals 2, 0, 2, 4, 6, or 8. It has to be one of those digits, otherwise the number is not divisible by 2. And we have that 5 divides n if and only if 5 divides the last decimal digit of n. And that means if and only if, when you look at this, the last digit has to be a 0 or a 5, because those are the only 2 single-digit numbers divisible by 5 in decimal. These are the first 2 tests. This is casting out 2's and casting out 5's. This is the divisibility test for 2's, which we get at using the black magic of congruence modulo m, in this case 2 and 5, with powers of 10. So we looked at powers of 10 when I divide by 2 and 5, and then looking at the fact that we write all integers as powers of 10 multiplied by decimal digits, we got a clever test for this. Now let's cast out 3's and see a divisibility test for 3. Okay, for casting out 3's, what we're going to do is, again, I have to write this every time, but n is dk 10 to the k plus dot 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 plus d1 10 plus d0. This is how we're writing integers. Then what we earlier, if you're taking the history of math class, we did this in all bases. So you can write this in any base b larger than 2. But we do it in decimal classically because most of our species does it this way. So we note that, again, 10 is equal to 3 times 3 plus 1, which says, and 1 is equal to 0 times 3 plus 1. So 10 is congruent to 1 modulo 3. That's extremely useful for us. What does that say? By property 8, that says that 10 to the k is congruent to 1 to the k, which is always 1 modulo 3. So powers of 10 always leave a remainder of 1 when I divide by 3. Any power of 10 will always leave a remainder of 1 when I divide by 3. That's extremely useful when I write all numbers as powers of 10. What's that going to say for n? Therefore, n is equal to or congruent to dk 10 to the k plus dot 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 plus d1 10 plus d0 modulo 3. But now I know that 10s can turn into 1s. So this is congruent to dk times 1 to the k plus dot 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 plus dk times 1 plus d0 mod 3. And because those 1s are gone, I don't have to write those anymore. What does that say? N is congruent to dk plus dot 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 d0 mod 3. What are these things called? Decimal digits. What is this? The addition or the sum of these. So this is the sum of the decimal digits. The sum of the decimal digits is congruent to n when I divide by 3. What does that say? N and the sum of its decimal digits leave the same remainder when I divide by 3. In particular, that remainder will be 0, and 3 divides n if and only if 3 divides the sum of its decimal digits. What does that say? 3 divides n if and only if 3 divides the sum of its decimal digits. That's the divisibility test for 3, or casting out 3s. If you have any number, we'll do it in a second, or right there. This one has a 3 in it, this one doesn't. How do I know? Because 1 plus 2 plus 3, the sum of its digits is 6 in this case. And 3 divides 6, so 3 divides 123. But 7 plus 2 plus 1 is 10. 3 does not divide 10, so 3 does not divide 127. This is the test that we're getting at. Let's do an example, and then we'll end. And then we're going to switch. Once we do an example, we'll switch to the Ceasar cipher and then the Enigma cipher. All right, example. Decide if each n is divisible by 3. If n is 2, 4, 7, 6, 5, 3, again, the only interesting numbers are ones that end in 1, 3, 7, or 9. If they end in a 0, 2, 4, 6, or 8, we now know it's divisible by 2. And if it ends in a 5, we know it's divisible by 5. So if we're looking for prime numbers, the only prime numbers that we can have, which are odd and larger than 5, are going to be numbers that end in 1, 3, 7, or 9. So I pick numbers that end in those guys. Otherwise, they're even. It's really easy to check. If I have this horribly large, this isn't even a horribly large number, but I have this number in the hundreds of thousands or in the millions, how do I check? The fastest way is I look at the decimal digits. I look at 3 plus 5 plus 6 plus 7 plus 4 plus 2. This gives me 10. This gives me 10. And then this gives me 7. So that's how I'm adding it up. Or you can go straight across if you want, but group in groups of 10. It seems like we like to do that kind of stuff. So this is 27. 3 divides 27, so 3 divides n. Yes, 3 divides this number. There has to be a 3 inside there. If you do the long division, sure enough, 3 will divide it evenly and you'll get a 0 remainder. 2, 4, 7, 6, 5, 3. If I divide 3 in there, 2 goes into there 8 times, I'm going to get 24. Subtract, I get 0, I bring a 7 down. 3 goes into there 2 times, I get 6. Subtract, I get 1, I get 16. I'm going to get a 5, I'll get 15. I subtract, I get 1, I get a 15. I'm going to get 5, I'll get 15, which is a 0. And I bring the 3 down, I'm going to get a 1. Well, the remainder was 0. So there is a 3 in there. But this is a much faster test, especially when the number gets bigger and bigger. This adding business is a lot easier to check if all I want to know if there's a 3 in there or not. For the next number, for 2, this was I for II. What am I looking at? 1 plus 5 plus 2 plus 1 plus 0 plus 1 plus 1 is 6, 7, 8, 9, 10, 11. 3 does not divide 11, so 3 does not divide n. So there's no 3 in this number, but there is in this one. How do I tell? I just add the decimal digits. Now let's get to, there's more divisibility tests. We can write divisibility tests. We can cast out 9s. We can cast out 11s. 7 is the one that causes us problems, but luckily 7 times 11 times 13 is 1001. So 10 cubed or 1000 is congruent to -1 mod 1001. So we get divisibility tests for 7 and 11 and 13 simultaneously. We'll do another video specifically on all of the divisibility tests at some point, but for now, we have casting out 2s, casting out 5s, and casting out 3s. Try to do this for powers of 2s and powers of 5s. There's a similar test. And then casting out 9s is awfully similar to casting out 3s. Casting out 11s is a little bit different, but 10 is congruent to -1 mod 11. So we get alternating sums of powers of -1s. Let's do the Ceasar cipher. Okay, now another application of congruence mod M. We don't actually need it for that, but the extension to the Enigma Machine cipher from the Ceasar cipher or shift ciphers is going to be extremely relevant. So we will turn these things into simple congruence mod 26 letters of the English alphabet anyways, Enigma Encryption Cipher. And then we'll generalize this to the affine ciphers or the Enigma Machine ciphers, and we can crack that Enigma Machine code as well. So Julius Caesar is fighting the barbarian hordes, and when he's doing this, he comes up with creating a clever cipher which shifts every letter of the alphabet back 3 when you list the alphabet. What's going to happen is, if we start suspecting that, again, the opposing army is not just going to tell you we use this kind of cipher, but if you start suspecting that we are the enemy or whoever's hiding the things from you is using a certain kind of cipher and you want to decrypt it or find out what it's saying, we suppose that we receive a message that's been encrypted with some kind of shift cipher or Ceasar cipher. Caesar specifically uses 3 as a shift. But if we think it's a shift cipher and we don't know what the shift is, first we have to find what that is. How are we going to find that? I'm given this cipher text message, which is encrypted. And so I don't know how to read it yet. I want to know what the plain text is. Oh, hi, Kitty. Oh. Kitty was outside, and then now she's inside and she's mad. So, she doesn't like it when she has her collar on. So how do we coincidentally get this word? Will be extremely relevant. She's one of them. And so what does this say? What I have to do is cleverly do this. Oh, and then I either have to speed it up or we will time lapse it. But I write one of the words cleverly vertically. Okay, Kitty, go. I take any of these words, but I'll use this one. Then what I do is I write out the entire alphabet behind each of the letters. So let's do that. And make sure you go all the way to the letter again so we can find out what the shift is. We'll do that in a second, just hang on. Now, what that does for us, once we've written this all out, we have one of the words. Sometimes it will happen that you might get in more than one English word. If that happens to you, just write out more of the cipher text vertically and find out which one it is, and it'll start forming an English sentence. So one of these columns has to have an English word in it. There it is right there. I've done it before, but cats. So FDWV this is the cipher text, we're going to call it. The hidden stuff, and this is going to be the plain text. And the best way, once we're doing this, to find out where we've gone, this is my job, your job is to decrypt usually, my job is to encrypt things. I'm going to hide them and then give you problems that say unhide them and tell you what it says. When I do that, we want to know how we went from the cipher text or the plain text to the cipher text. And what it looks like is just like Julius Caesar was doing 1, 2, 3. So we're shifting every letter back 3 in the alphabet, or we can do this modulo M, which is going to be 26, and then we can write this in a much more clever cyclic way. So what is this going to say? Long story short, when I do this, it will also say, I like cats. How are we going to get that? We now know that we've shifted every letter back 3 in the alphabet. So to find the Ceasar cipher key, we write out the plain text letters and then the ciphertext letters below them, and then we have a quick way of converting back and forth. I'll do that first, and then I'll show you how we're going to write this modulo 26. All right, so what we do to have the Ceasar cipher key is we write out the plain alphabet from A to Z, the plain text letters. And then what we've done is we shift every letter. So A is going to go to D. So basically what we do is move everybody back and then start at D and write the alphabet out again. When we get to Z, we loop around because there's 26 letters and we're going to turn them into numbers from 0 to 25. The remainders, when I divide by M equals 26 letters of the alphabet. But for now, this is the complete cipher key. So if we had the sentence that I just had, how do I make it? I say I like cat, so I becomes an L. So if you're encrypting, you start with the black row and turn them into the blue row. If you're decrypting, like I've given you, you start with the blue row and go the other way to get the plain text letter. So if I want I, that becomes, so if it's I like cats, then that's the plain text. If to get the ciphertext, I is L. So all I's are going to go to L's. L is an O. K is an N. E is an H. C is an F. A is a D. T is a W. And S is a V. If I want to go backwards, I say, well, I need an L, which is going to be an I. And then an O is going to be an L. And I'll get I like cats. This is how Julius Caesar was shifting everything back 3 to hide them. But we can go from anywhere from, if we do a shift of 0, then we haven't moved anything, so that's not okay. If we shift 26, that's mod 26, we just shifted back around through the alphabet again, so that's going to start looping around. So you can see why it's really good to talk about this modulo 26. There's basically 25 shifts we could do. A shift of 1 back or a shift of 25 back. If you go the other way, that's just doing negative in the modular arithmetic. You'll see in a second. So how are we going to write Ceasar ciphers modulo 26? Let's erase this and then we'll write the alphabet. What we're going to do is turn every letter of the alphabet now into a number, which is the remainder from 0 to 25 when I divide by 26. Then what we're going to do is write the shift cipher functions for every shift by B. Let's do that and then you'll see what I'm talking about. All right, so how are we going to create these shift ciphers, the encryption and decryption ciphers? How are we going to phrase this or articulate this using modulo 26? What we first do is now, instead of doing the shift like in the key for the Ceasar cipher, what we're going to do is create every letter of the alphabet being a number from 0 to 25. The remainders I can have when I divide by M equals 26. Then what we're going to do is, then if I shift back, if I call this the number 0, then turning A and shifting it back 3 into D is like adding 3 to 0. If I take F and I want to do it, it would be 1, 2, 3. It would turn into I. But now as a number, you can see I've just added what? I've added 3 to the 5 to get the 8. So now what we can say is the shift cipher by B, which is going to be in 1 to 25. The Ceasar cipher, specifically B equals 3. Then we're going to shift by B. So whatever the B is, it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, say. Then what we're doing is just adding 9 to that digit. Then this is going to be Y, and I'll explain in a second, will be congruent to X plus B modulo 26. Because if I'm going to take this guy and add 7, it'll be 1, 2, 3, 4, 5, 6, 7. So it's going to turn into a 2 modulo 26. So we can use our black magic arithmetic and turn big numbers into small numbers. Every number will be between the remainders between 0 and 25 when I divide by 26. What is this standing for? This is any ciphertext. So this is the plain text, guys. And this is the ciphertext guy. Encryption cipher. How do I decrypt? Well, in this one, it's fairly easy. And then the Enigma machine is going to be much more difficult because we're going to add an A in front of the X, which is going to be much harder to cancel using our modular arithmetic. But if I have this, Property 2 of the modular arithmetic says I can add or subtract on both sides. So let's subtract b on both sides. B minus b is 0, so it'll go away, and we'll have y minus b. So this will give us, if I subtract b on both sides, that will say x is congruent to y minus b modulo 26. This is the decryption cipher. This is going to be how we encrypt things, and this is going to be how we decrypt things. Again, because this is, we want, when we're decrypting, we want the plain text from the input of the ciphertext. The y, little variable y stands for the capital letters, all of the ciphertext letters, and x is standing for the plain text letters that we're trying to transform back and forth. Again, this seems like overkill for the shift ciphers because you could just play this game and add back and forth. But for the Enigma cipher, it's an extension of this guy where we're going to add an A in there. Let's do that again with the word cats, and then we'll encrypt it and decrypt it using now the machinery of modulo 26. Okay, so what we're doing now is we're taking all the plain text letters X, and we want to turn them into ciphertext letters Y. So I'm going to put the X's in here. These are the inputs that we're going to put into the encryption function to encrypt the word cats and turn it into a ciphertext word. How are we going to do that? Well, in each case, we're going to have C is 2, so we're going to have Y is congruent to 2 plus 3, which is 5. 5 is between 0 and 26, so 5, what is 5? That says this turns into, C turns into a 5, which is, oh, I'm supposed to do that in the orange. 5 turns into, 5 is an F. So again, 1, 2, 3, a 2 will turn into a 5 when we do this encryption function. If I now look at A, Y will be congruent to 0 plus 3, so this is a 3 mod 26. What is 3? 3 is a D, so A turns into a D. For 19, Y is congruent to 19 plus 3, which is congruent to 22 mod 26, and the S will be 18 plus 3, which is 21 mod 26. What are those turning into? The 22 is a W, and the 21 is a V. So that says cats turns into FDWV when encrypted. And if you want to get it back, we have to go the other direction and use the decryption function and subtract 3 from each value and get it this way. Again, this seems like overkill. I know, getting so nice. This seems like overkill at first. Oh, you can't smell the cat because it's not good for you. This seems like overkill at first, but when we now switch to the Enigma Machine cipher and add an A on the front here, we're going to have to know how to solve for X for the decryption, and then how are we going to be able to cancel the A if and only if the A and the 26 are relatively prime, and then we have to use the Euclidean diffusion algorithm to cleverly find this inverse and solve the Enigma Machine just like Alan Turing in 1942. Let's try that. All right, for the Enigma Machine cipher, what we're going to do is, again, we write all the letters of the alphabet as a number between 0 and 25, starting with A equals 0. A appears in a lot of words, and I like 0 when I do modular arithmetic because it kills everything. So A is 0, Z is 25, the biggest one. Luckily, Z isn't in my English letters, so you don't have to use 25 too many times, unless I mean and give you zoo as the word on your test, and then you have to translate all these. Anyways, what are we going to do with this? I have an encryption cipher. Now, a couple thousand years later, we jump from Julius Caesar fighting the barbarian Huns, the German armies in Gaul, etc. We flash forward to circa 1942. We're now in World War II, and the German army has the Enigma Machine, which is encrypting their messages. In 1942, we obtain a copy of one of the Enigma machines. We reverse engineer it with great effort, and then Alan Turing single-handedly decrypts the Enigma Machine cipher and invents the modern computer to basically solve and crack the Enigma Machine code. Here it is in all of its glory. We're going to explain this, and then we'll translate a couple letters back and forth, not whole sentences. This is why he invented the modern computer, to do this horrible process over and over again to translate all of the messages during the day. What are we going to do with this? we have an encryption cipher. This is what the Germans are using. There are going to be a whole bunch of them. You can use 0, I think, in here too, because we're adding the A in there. But we want to use this cipher, so now instead of the shift 1, we've added the A in front of the X. And we have to solve for X in this to get the decryption. That's going to be much more difficult than just subtracting B like the shift cipher. B is going to be any shift from 1 to 25, and the key to A to be able to find the decryption cipher is that we need the GCD of A and 26 to be 1, and therefore A will have what we call an inverse modulo 26, and we can solve for the decryption cipher, and this is the decryption cipher in and of itself. I'll show you how to get this S. This is going to be the Euclidean Byzantine algorithm. What we're going to do is, from the encryption cipher, we have to solve for X. When we do that, we get the decryption cipher is X is congruent to S times Y minus B modulo 26, where S and A S times A leaves a remainder of 1 when I divide by 26. That means that S and A are inverses of each other modulo 26. I should also point out, somebody will always comment that technically, yes, the Enigma machine was using the German language, which has 30 letters in the alphabet, but I teach you everything in English, so I'm going to use 26 and consistently do this in all my examples across the board. But historically, they were using an alphabet with 30 letters, not 26, so this changes it slightly. I'm just going to stick with 26 letters of the English alphabet. So how do we do this, and how do I find this horrible S? First of all, what you have to memorize is, Kitty. First of all, you have to memorize the fact that to go from here to here, what I'm doing is solving for X in this congruence. First of all, I'm allowed to subtract B from both sides from property 2 in those properties. But now, from property 6, if the GCD and A and 26 is 1, then I can cancel the A. How do I cancel the A? We multiply by some number S, so that S times A is 1. 1 times X leaves it alone, and we can isolate X specifically. So this is the decryption cipher from the encryption cipher. Then we have to see how to translate letters back and forth. Let's do that next. Right, Kitty? Okay, the best way to do this at first is by rote. So what I'm going to do is, suppose we're now given, also every 4 hours, I think the army is changing. Get out of my ear, Kitty. Every 4 hours, the German army is changing the cipher that they're using. So they're changing the Rolodex, and then they're using a different numbers in A and B. So our A here is the 11, and the B is a 5 from the general form. How am I going to solve for this? Well, first of all, I can do Y minus 5 is congruent to 11X mod 26. I can flip this around. Everybody, that bothers everybody, but I'm going to write it as 11X is congruent to Y minus 5 modulo 26. Now, to solve for the X, I need to get rid of 11, and I have to multiply both sides by S. I'm going to multiply the congruence on both sides of this congruence by S, but I need an S such that S times 11 is 1, leaves a remainder of 1 when I divide by 26. How are we going to do that? What I'm going to do cleverly is use the Euclidean Byzantine algorithm. From here, I need to find that number. We know that 26 is 2 times 11 plus 4. I'm going to find the GCD, which is 1. And then we know that 11 is also 2 times 4 plus 3. 4 is 1 times 3 plus 1, and 3 is 3 groups of 1 plus 0. So the GCD, the last non-zero remainder, is the GCD. And we now know we have our Euclidean Byzantine table. Kitty, where are you going? I need 3 quotients. So no, no, and 1, 2, 2 is what I need. 1, 2, 2. Then I get 0, 1, minus, plus, minus, plus, minus. This will be on 26. This will be on 11. 1 times 1 plus 0 is 1. 2 times 1 plus 1 is 3. 2 times 3 plus 1 is 7. What that tells me is 1, which is the GCD of 26 and 11, is 3 times 26 plus negative 7 times 11. What are we going to do with that? Now that the cat's gone, I can erase this. From this, what I wanted was, we're going to do the black magic of congruence modulo 26 now from this statement. So from there, we can write 1 is congruent to 3 times 26 plus negative 7 times 11 mod 26. Hit it modulo 26. but 26 and leaves its own remainder, leaves a remainder of 0 when I divide by itself. So 1 is congruent to 3 times 0 plus -7. I want a positive number. You can leave it as -7 if you want, but -7 plus 26 is 19 times 11 mod 26. And so what does that say? That says that this will go away, and 19 times 11 is congruent to 1 mod 26. So the S I need is 19, which is also -7. The inverse isn't unique. You can use any representative in that class. These guys are not equal. They leave the same remainder when I divide by 26, 19. And so this is the S I'm looking for. That tells me that I can now solve for the Enigma machine, this Enigma cipher, and then start decrypting messages if I had them. Therefore, one more time, solving for X in this equation, I'm going to get, this is 11X is congruent to Y minus 5 mod 26. I flipped it and subtracted 5 from both sides. Now to cancel this, I can multiply by 19. So we're going to get 19 times 11x is congruent to 19 y minus 5 mod 26. I've multiplied both sides of the congruence by 19, which I'm allowed to do by our properties. This we now know is a 1, and 1 times this is x. So we get the decryption cipher. X is congruent to 19 y minus 5 modulo 26. And we knew 19, the inverse of 11 modulo 26, has to exist because 11 and 26 are relatively prime, and therefore I know that we can write 1 as a linear combination and then therefore get rid of the term with the 26 in it and find the inverses of 11 modulo 26. This is the decryption cipher for this encryption Enigma cipher. Let's do at least one letter. If they encrypt a letter, how do I decrypt? I use this guy. All right, so now say I have a letter H, which is in ciphertext. So it's been hidden, it's encrypted, and I want to know what its plain text equivalent is. The plain text equivalent is going to be obtained by using, first I have to know that they were using this encryption cipher. Then I work hard like Alan Turing does to find the decryption function. Once I have that, I can now decrypt the encrypted messages. How do I do that? In this case, H is a 7, I see, as a number. And so I'm going to get, from this ciphertext Y, I'm going to get X is congruent to 19, 7 minus 5 mod 26, which is going to be X is congruent to 19 times 2, which is congruent to 38, which is congruent to 38 minus 26 is 12 mod 26. Once I have that, 12 is a number between 0 and 25, and I see, oh, that's an M. So what that says is it turned into, X turned into, the plain text letter was a 12, and 12 is an M. So that says H, the ciphertext letter, its plain text equivalent is the letter M. This is how I would change all 26 letters of the alphabet, or use a computer like Alan Turing does to quickly say, here's the one that they're using right now every 4 hours, here's the decryption function, here's all 26 letters of the alphabet, translate them into their plain text letters, and then start translating what the code is saying and read the messages. This is what's happening with the Enigma Machine ciphers. Please subscribe right here, hit the notification bell. I'll see you next time.